Welcome to section 14.5, curvature and normal vectors. Okay, the goal of this section is that we want to be able to compute the unit tangent vector, that's the first objective there, figure out what the principal unit normal vector is and what it means, and figure out the relationship between the tangent vector, the normal vector, and acceleration. If you combine all this together, what we're really trying to get at is what is curvature? When I have an object that's curved, I don't know, some like curved thing in space, how do I measure that this is curved more and this is curved less? Like this is more curvy. And then are there any other kinds of curvature? So this will say is like very curved, and this will say is not very curved. And then I also want to distinguish that, like, if I twist it this way so that it's not just curved but it's also twisty, that's a different kind of curvature. So by the time we get to the end of this section, we're hoping to have a good definition of curvature that lets us say that that's more curved if it's a tighter loop. And we want a definition of torsion that tells us that, well, yeah, you can be curved and you can also be kind of like curved, like twisted out of your curvature, and that's called torsion. So let's get into it. Today we'll mostly be talking about vectors. The previous sections had a lot of, there were some vectors in it, but we didn't get into like cross products and dot products of things as much in the previous sections. This section, we're all about taking cross products and dot products and magnitudes of vectors, so I put a little arrow there. But the main thing we're focused on is paths in space, curves in space, which are functions from the real numbers to the plane or from the real numbers to space. So those are the main data types we're talking about here. So let's recall that we think about a path as a vector valued function r of t, that's the position function at time t. And then if we take the derivative of the vector valued function, we get the velocity. And that velocity vector valued function gives us tangent vectors that tell us not just what direction we're going, but also how fast we're going. If it's a big vector, if it's a big vector, that means we're going very fast. So what's the unit tangent vector? Well, unit here is a key word. You've used it before when you had the unit circle. The unit circle tells you how big the circle is. And similarly, the unit tangent vector tells you how big this tangent vector is. It means that it has magnitude 1. Like the unit circle has radius 1. The unit tangent vector has magnitude 1. So we want to take our tangent vector that we know about, r prime of t, and scale it down so that it has length 1. So like if the vector had length 10, like speed 10, we would scale it down to have length 1. We would have to divide by 10. If the vector had length 30, we would have to scale it down by 30. So what you do is you take the tangent vector and you divide by its magnitude. So this is the velocity vector divided by the speed, which is a scalar. That's the unit tangent vector. Once you take, like the tangent vector has the direction and the speed information in it, but we've divided by the speed, so all that's left is the direction. When it's a unit vector, we imagine, we think of it as, yeah, we've gotten rid of the speed. This just keeps track of direction. Okay, now remember what the goal of this section is. We're trying to get at like what curvature is, so that like a tighter curve has more curvature, and that a loose curve has less curvature. So what is the unit tangent vector going to do for us? Well, the unit tangent vector tells us which direction the path is going. So we can hope that something that has more curvature would have its unit tangent vector changing faster. So somehow our curvature will come from, well, it's more curved if the direction you're going changes really quickly. So unit tangent vector tells us the direction we're going. Okay, here's our vector valued function that we can work with. The x-coordinate is t and the y-coordinate is minus square root of t. So this is going to follow the curve y equals minus square root of x. Yeah, we can get a quick graph of how this goes. Just because the x-coordinate is just t, then we can say that the y-coordinate is being determined based on what x equals. Like I have x equals t and y equals minus square root of t. but t is x, so y must be minus square root of x, which lets me plot the path easier. Okay, so this just asks us to calculate a bunch of things. So first of all, I'll do the simplest one first, which is r of 4. R of 4 is plug 4 in for t in all of these t's on both sides of this equation. So I'll get r of 4 equals 4 comma minus square root of 4. That's r of 4. What's r prime of 4? Remember not to make the common mistake of trying to take the derivative of a pile of constants. No. We'll take the derivative first, get r prime of t, and then plug in 4 for t. So I'll take the derivative of this vector valued function. And then I can plug in 4 to get r prime of 4, which is 1 minus 1 over 2 times the square root of 4. This is r prime of 4. Okay, let's find some more things. To find t of 4, it's probably going to be easiest to find t of t. Capital T here is the unit tangent vector. So it's going to be the same as the velocity vector, but scaled down by the speed. So let's get the speed. The speed is the magnitude of this tangent vector, so I'll have to do it the same way we find the magnitude of every vector. Square all the components, add them together, and take the square root. If I put this on a common denominator, I'll have 4t plus 1 over 4t. So if I combine these together, I can get that the unit tangent vector is the original tangent vector divided by the speed. Remember, all this does if you divide by a number is it scales the vector down. So I had a vector that included speed information, and I'm dividing by the speed to scale it down so it's a unit vector, length 1. Okay, so I need to divide 1 minus 1 over 2 root t by this factor here. Dividing by a fraction, like dividing by this fraction, is the same as multiplying by its reciprocal, so I'll split that up now. So I'll find its reciprocal and multiply by the thing I was multiplying by. That makes it more clear that like this 2 root t actually does something good in the y-coordinate. So the I component, the x-coordinate, I get 2 square root of t over square root of 4t plus 1. And in the y or j component, I get minus 1 over square root of 4t plus 1. So this is t of t. This is the unit tangent vector at each time. You can think of this as like, imagine you were driving on this path using misparameterization. The speedometer would give you the speed at time t. That would be this number. This is the speed. And then if you like had the compass, like you had a speedometer and a compass in your car as you were driving this path, the speedometer would give you this number, and the compass would point at the, like, it would show you the direction you're going. This vector, it's scaled down to be a unit vector, so it only has the information of what direction you're going. Finally, this question wants to know what t of 4 is, so I can just plug 4 into t of t. I'll get 2 times 2 over square root of 4 times 4 plus 1, and minus 1 over same denominator. The unit tangent vector should be going the same way as the velocity vector, but it should be a unit vector. So this velocity vector at time 4, how big is this vector? I guess it's like square root of 17 over 4 is its magnitude. The point is that this vector is a little bit larger than a unit vector, and t of 4 is a scaled down version of the velocity vector. So if I drew them both on the picture, oh good, that's what the question wants me to do. It's a good sign. Let's get it in blue or something. So here's r of t. The terminal point of r of 4 is right here. This is the point 4 minus 2. And then r prime of 4 is the velocity vector. It goes over by 1 and down by minus a fourth. So it goes over 1 and down minus a fourth. It gives you it's a tangent vector. It gives you the velocity of the curve. But the unit tangent vector, t of t, is a unit vector that points in the same direction. It's just been scaled down, so it's exactly length 1. So this one is t of 4. And this one is r prime of 4. I don't know if that's very clear from the picture. Essentially, if we zoomed in really close, we'd get that r prime of 4 looked like this. But it's a little bit too long. It contains speed and velocity. It contains speed and direction. And if you scale it down to be length exactly 1, you get t of 4, the unit tangent vector. Okay, let's look at the next page. So remember, what are we trying to do? We're trying to get at the curvature. We're trying to figure out, okay, you've got a curvy path. I want a number that tells me that like a sharp curve is more curved than a like long, wide curve. The curvature needs to be some number, and our plan is to figure out the unit tangent vector, because that gives us the direction. And we'll try to say like, how fast does the unit tangent vector change? So how can we use the tangent vector to describe the curve's shape? Well, the tangent vector tells us the direction it's going. If the tangent vector is changing very quickly, we would say that the curve has a lot of curvature. If the tangent vector changes quickly, the curve has a lot of curvature. So like low curvature, a low curvature shape would look like, well, it's barely curved at all. And a high curvature shape would be like spinning around a lot. The tangent vector tells us that, because here at the beginning of the low curvature curve, we'll have a tangent vector going this way. And then the tangent vector a little ways down is like basically pointing the same direction. It's only moving by a little bit. So the tangent vectors are similar to each other. They're barely changing. That's low curvature. Here, if I look at the tangent vector and then I go a similar distance down the curve, let's say that this is like a unit of 1. If I go another like 1 meter around this curve, the tangent vector has changed completely. It's like almost completely turned around in the other direction. For a high curvature curve, the tangent vector is changing really fast. It's like spinning around. Where for a low curvature curve, the tangent vectors are all about the same. So essentially we will just like make this our definition because it's pretty reasonable. We say that the curvature is going to be a lowercase kappa in the Greek alphabet. So it's not a capital K, and it's not a lowercase k. It's a lowercase kappa in Greek. It gets like drawn a certain way that it's curvy on the edges. So this is kappa. Okay, so this is the curvature. What we'll define it as is we will, I don't know if I've showed you this notation before, but if anybody ever puts a colon and then an equals, it means like a little bit stronger than just equals. If I write equals, it says the thing on the left is the same as the thing on the right. If I write colon equals, it means the thing on the left is defined to be this thing on the right. Like this is the definition of what I mean by the thing on the left. So yeah, let's see how fast the unit tangent vector changes with respect to arc length. So when I go, based on how far I go down the curve, how much does the unit tangent vector change? If the unit tangent vector changes really fast, that will mean I say it has high curvature. And if the unit tangent vector is barely changing, then I'll say it has low curvature. The problem is if I take the derivative of a vector valued function, I get a vector. I don't want the curvature to be a vector. I want the curvature to be a number. So I'll take the magnitude of this amount. So this is the definition of the curvature. The problem is that getting s into your calculations in practice is not very easy. So we will normally not use this definition directly, even though this is like, if you build curvature from the ground up, which was what we just did, you would say, well, get your unit tangent vectors, see if your unit tangent vectors are going all over the place. If they're going all over the place, then it has a lot of curvature. So you measure how fast unit tangent vector is changing and take the magnitude. But like, that turns out not to be the most efficient way to calculate it in practice, usually. So what we do usually is we say, okay, I know that the curvature is defined this way, but I'll use the chain rule to break that up and get everything in terms of t, because usually our parameterizations are in terms of t. They're time parameterizations instead of arc length parameterizations. Once you do that, well, ds dt is how fast the arc length is changing with respect to time. That's also known as the speed. Like, how much of the curve are you traveling per unit time is the speed that you're traveling around the curve. So I have this capital T prime in the numerator. And this thing is the speed, and we have a nicer way to write the speed. It's just the magnitude of r prime. And then I'll need the magnitude of this vector in the numerator to make it work out. So this formula is the way that you will actually end up calculating the curvature, usually. And this is the chain rule. Okay. The chain rule doesn't always work, so that's why we're careful about saying that we have a smooth parametrized curve without like corners and stuff. But in nice situations, you get to say that the curvature is this t prime, the magnitude of t prime divided by the magnitude of r prime. Okay, let's see it in an example. The easiest shape that is curved that we want to make sure, like we want to make sure our definition works. We want to make sure that like little circles are very curved and big circles are like not as curved. Because a big circle, if you looked at a piece of it, it would look like our low curvature example. And a little circle, it would look like our high curvature example. So let's find the curvature of this circle. Yeah, we've got our formula here, so let's just do it. So here's r of t. To get r prime of t, I just take the derivative. The speed is the magnitude of r prime of t, which I can get the same way I take the magnitude of any other vector. Square each component, add them together, take the square root. When I factor out the 9, I'll get the square root of 9 times 1. So the magnitude of r prime is 3. Now let's go get this thing in the numerator. The unit tangent vector is defined to be the velocity vector scaled down by its speed. And luckily, we just found both of those things. So if you follow this order of calculating things, then like things line up easily for you. So we need to divide 3 cosine t minus 3 sine t by 3. So I end up with this thing. Cosine t minus sine t. This is the unit tangent vector. The unit tangent vector means it's a tangent vector to the curve. We've got some circle here. And this is a tangent vector, but it's the tangent vector that's been scaled down to be length 1. It's the unit tangent vector. Now we want t prime of t in the formula, so I'll go get it. Take the derivative of t, and then I'm supposed to take the magnitude of t prime of t. This is a point on the unit circle, so I know what's going to happen here. Get 1. So when it says find the curvature, what am I supposed to do? Well, that's a weird kappa there. I'm supposed to take the magnitude of t prime of t, that was 1, and divide it by the magnitude of r prime of t, which was 3. So this circle, which is a circle of radius 3, has a curvature of 1/3. Okay, that's not a coincidence. If I had replaced this 3 in the question that made it be a circle of radius 3, if I had replaced that 3 with a different number, I still would have gotten exactly the same thing at the end. I would have gotten this 1 in the numerator, but I would have gotten a different number, whatever was the radius here. So what this means is that the curvature of a circle is 1 over its radius. This is the most likely way that you will use curvature outside of this class, because this is the easiest like engineering shortcut that gets you past all these formulas. If you have a physical real object, you are unlikely to have a nice parameterization of it. If it's like 3D printed, you'll have a nice parameterization of it, because that's how the 3D printer works. But if you don't have a parameterization, what you'll have is like a physical object, and you'll want to measure its curvature. What you do is you use this. You try to find a circle that has the same amount of curvature, and then use this formula. Let me show you what this looks like in like on a map. Let me pull up just a map of Elgin here. Let's just find like some off-ramp. This looks fine. So say I want to, this looks like the off-ramp between Lake Street and Villa Street, I think. Let me get it in here. Oh no. Well, good enough. What you can do when you have this like, let's look at this off-ramp. If I want to find its curvature, you could drive on it and find like a parameterization of it, and then use the formulas to figure out the curvature. But this is probably not the right way to go. Instead, you go, well, I know the formula for a circle, so let's just find a circle that's like about the same amount of curvature. Like a circle that would fit in the, I guess it's going to be bigger than that. The circle that would fit in the on-ramp nicely. Fighting with my program here, sorry. Looks like about... Hello? Oh. Okay, okay. I can do this. Well, we've got some circles here. Yes, I do want the move tool. So you build some circles that fit into the on-ramp nicely, and then you go get the scale of the map. And our formula for curvature of this on-ramp is... Where is it? Here it is. Our formula for curvature is 1 over the radius. So it looks like 2 boxes or so. So this far is 200 feet. So I've got like 200, 400, 600, 800, like about 1,000 feet. So I would estimate that the curvature of this on-ramp, or of this exit ramp, is... This is a huge mess on the screen, I'm sorry, but the curvature of this on-ramp is approximately 1 over 1,000 feet. And the units of this seem strange because it's inverse meters, or inverse distance, but the curvature of any object has this kind of units. And the curvature of a circle is 1 over the radius of the circle. Okay, let's onward to the next page. Okay, so we've got a definition for curvature. That was one of the big plans, was like, I want to know that a little circle has high curvature and a big circle has low curvature. And since the curvature formula is 1 over the radius, it's inversely proportional to radius, we got what we wanted. Now we're going to head down a path that lets us calculate torsion, which tells you the difference between something that's curved like this, where it's like kind of flat in its own plane, and something that's curved like this, where it has torsion. To get there, we're going to go like a level deeper. So now that we have direction from the unit tangent vector, like we're headed for the unit normal vector. Now that we have the direction from the unit tangent vector, how do we get the direction of the curve? What? That is it. What a weird question. Let's say, maybe they want to say, I think the question here that's being asked is how do we determine which way the curve is curving? I think that's the question. So like when you have a curve, you look at some some tangent vectors. This curve is curving to the right. And the way that we can try to tell that is we could say like, well, it's like we're kind of like curving this way. It's curving inward. So how do we calculate that? Oh my gosh, my vectors are so questionable. How we calculate the way that the curvature is curving is with the principal unit normal vector. So let's get that out. Why are all my notes in reverse order? This is not ideal. Okay, so the principal unit normal vector is called capital N. Just like the unit tangent vector is capital T, the unit normal vector, the principal one, is called capital N. We'll say that it's dt ds divided by the magnitude of dt ds. Okay, why would we do this? Well, the reason we would do this is we'd say, okay, dt tells us the direction we're going. dt ds tells us how the direction we're going is changing. If the direction is moving, is like rotating to the left, dt ds will point to the left. And if the tangent vector is changing by like going more and more to the right, then dt ds will point to the right. That finding dt ds will give us a normal vector. Now, to make it the unit normal vector, we have to normalize it. We have to like make it length 1, so we divide by its magnitude. So that's what we get here. This magnitude of dt ds, that already has a name. That's the curvature. So another formula we can get for this is that it's 1 over the curvature times dt ds. Notice that, this is the definition. Notice that the curvature is a number. This is a scalar, and dt ds is a vector. So I've got a scalar times a vector. I end up with a vector, capital N, the normal vector. Again, we've got s's all over the place, so we normally, puns on accident, we usually will not use this formula to actually calculate things. This is just like what makes sense. The formula we'll actually use is the formula that's in terms of t, and that goes like this. We'll find t prime of t and divide it by the magnitude of t prime. So this is a nice formula, but unless you happen to know the curvature or you happen to know you have an arc length parameterization, you will almost always use the second formula.